Welcome back everyone. So as motivated in the last lecture, what we are doing in control engineering or control systems is basically trying to manipulate the output of a system such a way that we get the output as we desire. So we will basically change the input signal to a system in such a way that the output is exactly as we desire. And the challenge of a control engineer is to design such an input. So when I told you about this motivation, you can see that I have used two words primarily. One is input signal or output signal and the other is system. So a very good point to start this entire course is from the definition of what a signal is and what a system is, because if we understand what a signal is well and what a system is well, then we can easily proceed to our actual goal, basically to get the desired output. What input should we get to give to a system? So we will start today's lecture with the definition of signals. So what is a signal? A signal is a function of one or more independent variables such as time, space, or even several variables used to convey information about some phenomenon. Now notice that I have used certain mathematical terms in the statement. Function, you already know what a function is. Okay, a function will have an independent variable or several independent variables, which when you change you get the value of the function. So as example, if I take say f of t, so t here becomes your independent variable. So when I change the value of t, you will get some value of the function. So suppose f of t is equal to sine t. So as you change the value of t, which is the independent variable, you get the value of the function. So what we have done in this definition is that we have taken a physical quantity, which is a signal, and we have represented it with a mathematical object. And why are we doing that? Because if we represent a physical quantity with a mathematical object, we can do the analysis on that mathematical object on a pen, on a paper, or on a computer, and then see how it will behave without affecting the physical system. And then after we are satisfied with what we wanted to do with the system, mathematically whatever results we get, we try to translate that back into the physical system. So that is what a signal is. Now where can you see signals? Example, in electrical circuits, if you think about say a RLC circuit, whether a series RLC or any other configuration, you give inputs to the signal. Input signals can be voltage signals, and output, say you are taking the voltage across some capacitor, say, so that will become your output signal. So physically, if you would have made the circuit on a breadboard, so you would have given input to the system from some source, and then you would have checked the output maybe with a DSO or a CRO or a multimeter maybe. So the physical quantity here would be, in the signal here would be, input signal would be voltage signal, output would be voltage signal across the capacitor. You can similarly have current signals as well. Then in case of mechanical systems, you can have position or speed as a function of time. Consider an example of a say quadrotor, which is an electromechanical system. So in that system, if you take a quadrotor, here we have a quadrotor with us. Say quadrotor has 4 rotors or motors, okay, and when they rotate it flies because of the thrust and all. We will get into details of how a quadrotor works later in this course, But think about this quadrotor. Suppose it is moving in space. Okay, you can time the position of the quadrotor. So suppose at t equal to 0 seconds it is at this position, at t equal to 0.1 second it moves forward, and for each and every point, every time interval, say 0, 0.1, 0.2 or some other intervals, you find out what is the position of the quadrotor with respect to some coordinate system. Now the function that you get would be a position function. So it would be something like, say, p of t. So at p of 0, suppose the quadrotor position was 0, 0, 0 in 3D space. At p 0.1, suppose it is at 0, 0, 1, and so on. So in this case, the time variable is changing from, the independent variable time here is changing from t equal to 0 to 0.1, 0.2 and all, and corresponding to that the output of this function is a 3D coordinate which is giving you the position of the system. So this also is a function of time, this also is a signal, it is a position signal. In the same way you can also get to the velocity, you can also find out the velocity signal. What can be other examples of signals? In imaging, okay, you can also have signals in imaging. For example, if you have an image, okay, where suppose you have a black and white image, and you find out at different points what is the intensity of black, is it black or white, the pixel intensity, okay, and that will form a signal as well. Now in this case what will happen is, the independent variable, you have two independent variables, okay. So for example, suppose this is your image. So if I say this is your x-axis and this is your y-axis, so for different points you will have different values, pixel intensities. Based on that pixel intensity you will have some values, okay, and so this is a function, this image, say this image is a function of x and y. At different values of x and y you will have different pixel intensities. I will show you this with an example. So here what I have done is, this is a MATLAB code. So this code IMRead is used to read a image. So as we go ahead with this course, at different points I will be using MATLAB codes, and I will also be explaining them so that you can use those in your day-to-day problems that you will face. So I hope that will also help you in implementing what we learned in this course. So suppose I have an image.png, okay, I have named that and I am reading that image. Now what IMRead is doing, it is taking that image and storing the values, pixel intensities as a matrix, okay. So let me first show you, let me run it and show you. So this is the image that we have, okay, and you see what I have done is, I have read that image and put it inside a variable. So let me see what the variable is. So if you write img, you will see the variable. Look at the variable. So you can see on the right, the variable is a 1024 cross 1024 size image. Basically there are 1024 points on the x-axis and there are 1024 points on the y-axis, okay, and at different points what is the pixel value, pixel intensity is shown here. So for example, you see 255 means black, okay. So if you go up, let me just go up, you see these are the points where we had that smiley face, okay. Let me show you the image again. This is the image. See, these points will be zeros. So the smiley face, the intensities are different there, zeros and ones will be there, so zeros and ones are there. So this is a signal where you have two independent variables, x and y, okay, and the signal here is an image signal, okay. So what are the different types of time domain signals? So see, in this course most of the time we will be talking about time domain signals only. So what do you mean by time domain signal? Time domain signal means the independent variable is time, okay. So when we are representing the signal as a function, the independent variable is time. So there are two types of time domain signal. One is continuous time domain signal and the other is discrete time domain signal. So what is a continuous time signal or a continuous time domain signal? So a signal which is defined at each and every value of t. So for example, if I say V t, suppose it is a voltage signal. So here note that t is a real number, right? It can vary from 0, even negative numbers, but let us start with 0. So it starts from 0 and then you can have any value you want to, 0, 0 0.001, 0. Whatever values you want to, and it is a continuous variable. So if you have a continuous variable and at each and every point of t you have Vt, then we say that it is a continuous time signal. And what is a discrete time signal? A discrete time signal is one where the variable, the independent variable has discrete values and at each discrete value you have the function value. That is a discrete time signal. The example of position that I gave, where I was checking the position every 0.01 second of the quadrotor, that was an example of a discrete time signal because the time value was there from 0, then 0.01, then 0.02 and all. Okay, fine. So this is what basically signal is. Okay, in this course most of the time we will be talking about continuous time signal, but note that in practice whenever you use any kind of signal, at the end of the day what you will do is you will take the signal and then you will try to take the data of the signal in your PC, in your computer or in some processor, and then try to work on it. Now if you have a computer, it is actually a digital device, so it cannot have continuous time signal, it cannot store continuous time signal, so we will have to sample the signal. Okay, so actually most of the times what we do, whatever processing we do on our PCs are all in discrete domain. Okay, most of the times, no, it's always in discrete domain. So although we should, then you can always ask me the question, then why are we even learning about continuous time signal? It turns out that from continuous time signal, if you learn the concepts in related to continuous time signals, then that can be easily used for a discrete time case. Okay, and hence we will go for continuous time signal, and later on when I will be explaining you the simulations or whenever there will be a need to understand the discrete time part of things, I will try to explain that. So that is what signals are. So now let us move to systems. So what is a system? So system is basically, you can think of it as a box or a collection of components, okay, to which you give some input signal, the components changes that input signal and then gives you some output signal. Okay, it is almost like a machine, you give something inside, it takes care of that signal and then gives you out something. Okay, so that is why you will have an input and an output. Now like in case of signals, we had a mathematical object related to signals. The mathematical object was function. Okay, so can we do the same for systems also? Because if we have a mathematical object related to systems, to define systems, then it will be easier for us to analyze systems, and of course we have that, and that is how we define a system. A system is mathematically represented as an operator. It is an operator or a function that maps input signals to output signals, described by equations, transformations or rules. So the mathematical object that we are talking about here is an operator. Okay, a system is mathematically represented as an operator, a signal is mathematically represented as a function. So how do we write it mathematically? So input is a signal, so we write ut. Ut is the input signal, say in time domain. Okay, and output is yt. So we will use y for output throughout the course and u for input throughout the course, and the independent variable will always be time. Okay, so this is the input, this is your output, and then what is the system? The system is represented by an operator. Okay, we are writing the operator as this. So what is this operator? So go to the definition. Typically if the input is ut and the output is yt, the system is denoted as yt equal to h of ut. So you see, h takes ut as its input argument and gives some output. Now here h denotes the transformation or operation performed by the signal on the input signal. So a simple example of a system can be, suppose you have an integrator. So what is this system? It takes ut as input, okay, and then gives out yt. And what is yt? Yt is nothing but the integration of ut, say from 0 to t. So this is an integrator system. So here the transformator or the operator here is an integrator or an integration operator, okay. So it's an integration operator here. This is an integration operator, okay. Now we have seen what do you mean by signals as a mathematical object, and now from here in the next lecture we will see what are the different types of systems that we will be dealing with in this course. Thank you.